Hi friends, welcome to my channel. Let's have a look at problem 2354, number of excellent pairs. So in this video, we're going to share a method based on computing a bitsum and frequency dictionary, and then we do simple counting. So this problem requires to return the number of distinct excellent pairs. So the excellent pair is defined as here. So a pair of numbers, let's see, num1, num2, is called excellent if the following two conditions are satisfied. First, both the two numbers exist in the array nums, but this condition does not require the two numbers are different. So the second condition is that the sum of the number of the set bits in num1 and bitwise or num2 and num1 bitwise and num2 is greater than or equal to a given threshold key. So here are some examples. So in example 1, so the output is 5, and in the explanation it lists the available excellent pairs. So notice that 2, 3 and 3, 2 are different pairs. So in example 2, so the output is 0 because the sum bit should be 10. The constraints on this problem are mainly on the length of nums array, so which is bounded above or can be reached to 10 to the power 5, which is a decent large number, and the k is in the range between 1 and 16. And each num is in the range 1 and to 10 to the power 9. So actually 10 to the power 9 it's if you compute the logarithm, so it's less than 30. See, so if we compute a bit sum, so the bit sum actually is bounded by a small constant. Let's see, 30 plus 30, so 60, right? So that's why also the k is less or equal than 60. So with that said, I guess we are ready to look at the method. So as we mentioned, so the method is to compute a bit sum and frequency dictionary, and then do simple counting. So first, let's be aware of a simple fact, that is, for two integers mn, so the bit sum of m or n plus the bit sum of m and n equals the bit sum of m plus the bit sum of n. So this formula actually is very easy to observe, I would say. So here, if you would like to prove it, or just do a quick verification, so actually the verification or the proof is reduced to the situation that we consider one corresponding bit position in m and n. So as such, so it reduces to consider the three cases, that is m equals 1, n equals 1. The second case is m equals 0 and n equals 1. So, or the third case is m equals 0 and n equals 0. So actually we can verify the formula for the three cases, then it holds for all integers m and n. So that's the fact. So now let's look at the observations here. So first is that same elements do not produce new excellent pairs with another number. So here is an example to fix the idea. Suppose we have 3, 3 and 1. Then the first occurrence of 3. So if paired with 1, it forms 3, 1 or 1, 3. Then the second occurrence of 3 yields the same pairs. Therefore, we just need to consider the set corresponding to the nums array, right? So from now on, we're going to talk about the set of nums. So secondly, the same number can pair itself based on the problem statement. So in statement 1, as we mentioned, we do not require nums1 and nums2 are different. So this can also be seen from example 1, because 3 and 3 paired with itself. So that's the second observation. So next, how do we do the counting? So assume we have two bits sum, let's say S1 with frequency K1 and S2 with frequency K2, then their contribution to the final count is nothing but 2 times K1 times K2. So 2 means that we care about the order. So AB and BA, if AB are not the same, so they are different pairs. So with that said, I'm going to present two solution formats. The first one actually is from scratch. The second one is a little bit shorter. So first, I'm going to implementation from scratch. So for this, I'm going to compute the sum bits for each number. So for this, let's write a small function maybe. So let's define bit sum. So here I'm going to accept a number. Let's call it m. Then what we want to do is that we set a temporary variable called result. We want to count how many 1 bits in the num. So this is basically a while loop. While n is greater than 0, then we do a division with remainder. So let's say qr equals divide div mode n with respect to 2. If r equals 1, then we are going to increment the result by 1. Otherwise, so we do nothing. And then we are going to reset the state of n by q. So that's it, right? So we're going to return the results. So this small function actually counts the bit sum for each integer given. So with that said, we are ready to do the frequency count. As we mentioned, we're going to consider a set of nums. So we just do this. So this is the routine. So let's regard this one as step 1, hyperfunction. So notice that in this problem, so the requirement is that all the numbers positive. So we do not need to consider n is less than 0 or equal to 0. So this is step 1. Now let's look at step 2. So we are going to compute the bit sum and frequency dictionary, right? So in order to get this information, I'm going to first initialize an auxiliary dictionary to help, and then we're going to traverse the set. So for y in S, then we're going to get the bit sum. Let's call it k. That is bit sum y. Then we're going to update this frequency. So basically it's aux k equals aux. First we check if the k is inside the dictionary. Otherwise we're going to set the frequency to be 1 and then plus 1. So that's it for the bit sum and frequency table. So finally, so we do the counting. So for doing the counting, so this is actually very routine. So we just need to initialize a result. Let's call it initialize at 0 first. And then we are going to traverse the keys. So for K1 in aux and for K2 in aux. Then we're going to check if K1 plus K2 is greater or equal than the threshold value K. If so, we're going to increment the result by aux K1 times aux and K2. That's it based on our counting here. Then we're going to do the return. We're going to return the results. So that's it for a format of solution. So let's do a special case check first. Yeah, it passes a special case. Now let's do a generic case check. Yeah, it passes the generic case. So let's regard this one as version 1, and let's do a shorter version once we realize the logic here. So what we want, actually essential here is the bit sum and the corresponding frequency. So we just need to get the bit sum frequency, right? So for this, we can call collections counter. So then we can write a list comprehension, for example, item. So we're going to use the bit count function. So for item in set nums. So this way actually we got the aux dictionary as in version 1, and then we're going to do the count at result equals 0, and then we're going to iterate. So for key 1 in bitsum frequency, and for key 2 in bitsum frequency, and then we are going to check if key 1 plus key 2 is greater or equal than key, right? If so, we are going to increment the result by the product, that is bitsum frequency key 1 times bitsum frequency key 2. Then we are ready to return the result. So let's see if it works. It passes a special case, and then let's do the generic check. So it passes the generic case. So here actually we can use some other format. For example, let's change this line a little bit. So we can use so for example the map function. So here I'm going to map. I'm going to do a map, and then we're going to use, let's say, int bit count. So it's a callable, right? So we're going to apply this to the set. And then it will give us a iterable. So map int. So that's it. So let's do a check. So invalid sentence. So you got a comment. Let's see, map int bit count set nums. Let's see if we miss something here. Map int bit count set nums. So we are missing a parentheses. So now let's do a check. Yeah, it passes this case. Now let's do a generic case check. Yeah, it passes all the cases. So if we like, actually we can write it even shorter. So for example, we can write it in one line if we like. So let's see. So let's return sum of let's do things like this. Sum bitsum frequency key 1 times bitsum frequency key 2. Let's see. For key 1 in bitsum frequency, and for key 2 in bitsum frequency, we put a filter. The filter is if key 1 plus key 2 greater or equal than key. So let's see if it's good. Yeah, it passes a special case. Now let's do a generic check. Yeah, it passes all the cases, but I would say, so here the nested list comprehension is sort of confusing in sometimes for people. So that's basically about it for this problem. So I guess personally I like the first solution very much, because we implement from scratch, and which help us to understand the finer details. So with that said, I guess that's all about this video. Thank you so much.